Hey everybody, your Friendly Math Tutor here with our Unit 2 Basic Differentiation lecture. So today we're just going to look at all the key concepts and then examples of those for Unit 2. Also remember to check out our Instagram, Facebook, Patreon, TikTok. They will all be all week long. Will be loaded with videos and examples and practice problems related to this topic. All right, so let's jump in. So what we're going to start with is the idea of average rate of change. You just want to think of average rate of change is just the slope of what we call a secant line. So a secant line is a line that goes through 2 points on a curve. So if we have this f of x equals x squared, then the secant line is going to be the line that goes through those 2 points. This point on the curve is 1, 1, because 1 squared is 1. And this point is 3, 9, because 3 squared is 9. And if we want to find the average rate of change, that's just the slope of the secant line. And we remember slope is just y2 minus y1 over x2 minus x1. So we get 8 over 2, which is equal to 4. So we would say that the average rate of change of this function from 1 to 3 is 4. If we take a look at an example of that, then this, again, this is a graphical example, so we get an idea that it's the slope of the secant line. For this one, we're just given some function, and it says find the average rate of change. Well, average rate of change you're going to start to see is just this formula, f of b minus f of a over b minus a. All that is the slope formula. It's not a brand new formula. It's y2 minus y1 over x2 minus x1. It's the same thing. So if we do that here, it just is f of 4 minus f of 1 over 4 minus 1. F of 4 is just plugging into this function. So 4 squared is 16, plus 2 times 4 is 8, 16 plus 8 is 24, plus 3 is 27, minus f of 1, that's just 1 plus 2 plus 3, so that's 6, over 4 minus 1, well that's 3, so this simply just is 27 minus 6 is 21 over 3, so we get 7. All right, so the average rate of change of this function on this interval is 7. It's increasing kind of 7 units at a time is what we can look at that. Or if this were time, it'd be 7 units per second. All right. So then what that does is that leads to instantaneous rate of change. What instantaneous rate of change is the slope of the tangent line. So let's say we have this tangent line here. Let's pretend that that's a straight line. This line is what we call the tangent line. All right, this line that goes through 2 points is the secant line. This line is the tangent line. All right, so the slope of the secant line is average rate of change. The slope of the tangent line is instantaneous rate of change. It's the rate of change at this exact moment. This is the rate of change over a period of time longer than a moment. And that's, again, average rate of change, secant line. Instantaneous rate of change, tangent line. But the thing is, we don't have a good way of finding the slope with going through 1 point because algebra tells us we need 2 points. So what we do is we do start with this, the slope of this secant line. And what that is this point here is when you plug in f to just some function, I'm just going to call this f of x, then you get f of x. If you plug in x plus h to that, you get f of x plus h. So if I want to find the slope of this dashed line, which is the secant line, that is back to this formula, that, or just our regular slope formula, that is f of x plus h minus f of x over x plus h minus x. We simplify this a little bit. That is f of x plus h minus f of x over x, the x's cancel, and we're left with just h. Okay, so that gives us the slope of a secant line in general. But what if this h we make smaller and smaller and smaller? As we make this h smaller and smaller and smaller, this point gets closer and closer and closer to this point, which then the slope of the secant line gets closer and closer and closer to the slope of the tangent line. Well, what did we go over last week that allows us to use this idea of getting closer and closer and closer, and that's limits. So we're going to take the limit of this thing and we're going to make h go to 0. And this whole thing is what we call the definition of the derivative, or the slope of the tangent line, or the instantaneous rate of change. They are all the same thing. Derivative, slope, instantaneous rate of change, they all essentially mean the same thing. So to put this in practice, to look at an example, let's say we have this function and we want to find the derivative. So that's f prime of x. That's the derivative of f. So we have these functions, and then those functions have their own derivative. And the beginning of this is we have to do it the long way. So using the definition of the derivative, that is the limit as h goes to 0 of f of x plus h. Well, that means we go to our function and we substitute every x with x plus h. So we get x plus h squared plus 2 times x plus h plus 3. That represents f of x plus h. Then we subtract our function. So we're going to subtract the function that we have, x squared plus 2x plus 3. And then all of that is over h. Now we're going to clean this up a little bit, so we're going to square this out. X squared plus 2xh plus h squared. Then plus 2x plus 2h plus 3, distribute the negative, minus x squared minus 2x minus 3. Whoops, all over h. We get a bunch of cancellations. X squareds cancel, 2x's cancel, 3's cancel. And then what we can do is, I do have x here, that is wrong. It should be as h goes to 0. So the limit as h goes to 0, all of our terms, 2xh, h squared, 2h, all the terms that remain, they all have an h in it. What I can do is factor that h out and divide by this h. So then I'm just left with 2x, so this h divides with that. Then I have to take an h from this and divide it with that. And then this h divides with that. And finally, if I take the limit as h approaches 0, I get 2x plus 2. So we say that the derivative of x squared plus 2x plus 3 is equal to 2x plus 2. And if I want to find the instantaneous rate of change at x equals 2, I just now substitute 2 into here. So essentially I'm finding f prime of 2. 2 times 2, 4 plus 2 is 6. So the instantaneous rate of change over this function at 2 is 6. Okay, so we've got average rate of change, slope of the secant line, algebra 1 concept, just rise over run, y2 minus y1 over x2 minus x1. Then we introduce limits, and we take the limit of the slope of the secant line as the distance between these points gets smaller and smaller and smaller. And now we introduce calculus, and we can find the instantaneous rate of change at a specific value by finding this thing called the derivative. All right, let's move on. So the next thing we're going to talk about is the idea of differentiability and continuity. So we talked about continuity in Unit 1, and how we're going to kind of look at this is eventually we'll get to an example where we're going to find the points where something is differentiable and where it's continuous. So we talked about last week, continuous is where if you draw the graph, anywhere you would have to like lift up your pen or pencil, that in those places, it won't be continuous. So let's just review that real quick. So we've got 3 basic examples where something is not continuous. One of them is a hole, and we called that a removable discontinuity. The other one is something like this, where we have a jump, literally the function jumps, all right? So it's not continuous there. And the last one we looked at was something called an infinite discontinuity, which is really just a vertical asymptote, all right? So we have infinite. Now, anywhere that something is not continuous, that means that it also tells you that it's not differentiable, which just means you can't take the derivative at that point. The derivative is the slope of a tangent line, all right, of the curve. If something is not differentiable, it means it has either an undefined slope or it just doesn't have a slope at that point. So if you have any one of our three main types of discontinuities, it is automatically not differentiable. You will not be able to take the derivative at a hole, at a jump, or at a vertical asymptote, all right? Those derivatives will not exist. It won't be just a numerical value to represent a slope. Now, in addition to that, there are several different types of problems where something will be continuous. You can draw it without lifting your pen or pencil, but it won't be differentiable. So those ones you have to look out for look like this. This point here, we call that a corner. There's a sharp turn. The slope from the left and the slope from the right are so vastly different that they're on the graph of the derivative, there would be this jump. It's not like the derivative itself isn't continuous. This is continuous though. I draw it here and then I draw it there. Doesn't fit one of these, but it's still not differentiable, all right? Another example is very similar to a corner. It's just curved on both ends. We call this a cusp, all right? At the cusp, not at those other points, just specifically at the cusp in the corner, again, we have a continuous function, but the derivative itself is not continuous. So at that point, we would not have a tangent line. We would have an undefined derivative. The third important place is harder to spot, but it would look something like this. So if you think about, and I'm looking at this point right here, what I just drew as the dashed line is that would be the tangent line. So if we think about a tangent line is the slope of the tangent line is what the derivative represents. Well, if the tangent line itself is vertical, the slope of a vertical line is undefined. So therefore, you can't have a derivative there. So you've got a couple of examples. So the reality is, and here I'm going to call this a vertical tangent. So you've got 6 cases here where they're not differentiable. The first 3, it's not continuous, which automatically means not differentiable. The second 3 are examples where something is continuous. It's a continuous function, but the derivative itself at these specific points is not going to exist. You can't even come up with a single tangent line for these that would work. Here you can come up with a tangent line, but the tangent line itself has an undefined slope, so it would not be an actual value that we could say, well, the derivative is 2/3 here. We can't say that in any of these cases, so we say it's not differentiable. So if you just look at our example, and we want to figure out where is something not continuous or differentiable. That would happen here at -3, because we have a jump, so it's not continuous and not differentiable. It would happen here at 1, because it's a hole, so it's not continuous, therefore not differentiable. And it would happen at 3, because there's a vertical asymptote, so it's not continuous, therefore not differentiable. Then we have this other category where something can be continuous, but not differentiable. That happens here at -1. It's continuous. I can draw it here, and then I can keep going. But at -1, it's not differentiable. It's kind of like a corner end cusp. So any of these sharp turns. And then again, I'm going to say at 5. These are harder to see, but at 5, it looks like we could have a vertical tangent. So at 5, again, it's continuous, but it's not differentiable, all right? So we end up with not differentiable at 5 different points along the graph, or 5 different x values, and 3 of them are not continuous, leading to not differentiable, and 2 of them are continuous but not differentiable. All right, so I hope that helps. Just you have to be able to identify from graphs when something is not differentiable or when it's not continuous, and in understanding that relationship is super important. All right, let's move on to some derivative rules. So today we're looking at basic differentiation. So we looked at earlier how we had the slope of the secant line became the tangent line when we took the limit as the distance between the 2 points went to 0. But that could take a while to do the definition of the derivative all the time, over and over and over again. And you'll see through the other examples that we do on TikTok and some of the other platforms, there's certainly ways that you could be tested to have to use the definition of the derivative. But for the most part, now that we kind of move on from that and we start to learn like quicker ways to take the derivative. So we start with the constant rule. So if f of x is 7, you want to really think back to algebra. When you have the graph of a constant, that's just a horizontal line. Because if it's always 7, then you just draw a line across so that your y value is always 7. Well, if you think about the slope of that line, the slope of a horizontal line is 0. So if you have a constant, you will have a horizontal line, and the slope of a horizontal line is always 0. So the derivative, f prime of x, is equal to 0. So the derivative of a constant, 0. Now we look at a linear term. So 4x, right? We know that's linear because it's 4x to the first. And what you want to think about for that one is, again, derivative is slope. A line has a constant slope throughout the problem. It doesn't have a different slope at one point than it does the other. That's what makes it a line, a constant slope. Well, the slope of this is just 4. So the derivative must always be 4. It doesn't matter what point we're at on the line, the slope will always be 4. It's not changing. So the derivative of a linear term is always just the slope, which really is just the coefficient. So that when you have x to the first, the coefficient of x is the derivative, all right? So we see 2 examples where the derivative doesn't have an x in it. It's always the same. Horizontal line, it's always 0. Linear, it's always just the slope, which is the coefficient. Now we look at, let's say we have x to a different power. There is this thing called the power rule. This is one of the most important things you'll ever do in calculus. The derivative using the power rule, and then we'll see in some examples over here, is you bring the exponent in front and it becomes your coefficient. If you have a coefficient already there, unlike I have here just a 1, you are actually multiplying that by whatever is already there. Again, we'll see that in some examples. And then the new exponent reduces by exactly 1 unit. So it becomes n minus 1. All right, so the power rule is anytime you have x to a power, and again, the power becomes the coefficient or gets multiplied by whatever coefficient is there, and then you lower the power by 1. This works for every single power, and we're going to see that in our examples. So then we look at the sum and difference rule. The way the sum and difference rule works is that if you have adding and subtracting and you have different terms, so here I have 5 terms separated by addition and subtraction, then what you can do is you can just take the derivative of each of them individually using these 3 rules. So the derivative of this function, well, the derivative of x to the 4th, we're going to use the power rule. We're going to bring the 4 in front, and we're going to lower the power by 1. So the derivative of x to the 4th is 4x cubed. Now, this one, when I bring the 3 in front, there's a 3 already there. They get multiplied together. So that's going to give me 9x, lower the power by 1, squared. The 2 comes in front, multiplies by the 7 to give us 14. The power of 2 lowers by 1, giving us 1, and I don't have to write that. Now I've got my linear term, negative 8x. Well, the coefficient is just negative 8. Or if you think of if you had the graph of negative 8x, the slope would just be negative 8. Now I end with a constant. Well, the derivative of a constant is 0. I don't have to write plus 0. So this ends up being the derivative. here, well, I just wrote equals. This should be f of x. Let's say we're going to do the derivative here, but I want to rewrite some of these. So we go back to some algebra 2 or pre-calculus, and we think, well, the cube root of x squared, the way I can write that is x to the 2/3. If we remember, the power over the root is where a rational exponent comes from. And if you have an exponent in the denominator, you bring it up, and that's what a negative exponent is. So we have 2x to the negative 3. The 7x squared minus 8 remains unchanged. Now I'm going to take the derivative. Well, for rational exponents and negative exponents, the point of me doing this problem is to show you the power rule still works. I bring the 2/3 in front, and I subtract 1. I always subtract 1. Well, 2/3 minus 1 is negative 1/3. Now here, I bring, for negative exponents, it still works. I bring the negative 3 in front, multiply by the 2, and I get negative 6. And I lower it by 1. Well, negative 3 minus 1 is negative 4. Now I just do the same thing as I did back in this problem. 2 times 7 is 14. X to the first. Derivative of negative 8 is 0 because it's a constant. So I have this answer. Maybe you want to rewrite it back in the other form, depending on the problem. So this would be 2 over 3 cube root of x. I moved it to the bottom because it's a negative exponent. This is minus 6 over x to the positive 4. And then I just have plus 14x. All right, so that's how we can use some of our basic rules to take derivatives of functions that have just addition and subtraction in it. Okay? All right, let's move on to some derivatives of common functions, and then we'll talk about product rule and quotient rule. So here we've got 8 functions that you are just going to have to know the derivative of them, all right? And that is sine of x. The derivative of sine of x is cosine. The derivative of cosine is negative sine. So notice they kind of go together. The derivative of tan is secant squared. The derivative of cotangent is negative cosecant squared. The derivative of cosecant is negative cosecant cotangent. The derivative of secant is secant tangent. The derivative of natural log x is 1 over x, and the derivative of e to the x is itself. All right, so just a couple of things. This isn't really mathematical, but all of these functions, trig functions that begin with the letter c, those derivatives are negative. So again, that's just something that might help you when you're kind of memorizing these. Sine and cosine go together, so sine is cosine and cosine is sine, except it's just negative. Tangent goes with secant, so tan is secant squared, and secant is itself times tangent. And then you could also think tan kind of goes with cotan because they mirror each other. They are each something squared. Cotan is negative. And then cotan also kind of goes with cosecant because it's cosecant squared. And cosecant is like secant in that it's itself times another function, and the other function that it is multiplied by is cotangent. So you can kind of see all these little relationships in here that should help you. Instead of just blindly memorizing them, you can kind of see those relationships, and hopefully it can help you learn these. And then again, ln, you just need to know is 1 over x, and e to the x is itself. All right. So now we're going to use those in product rule and quotient rule. So earlier we saw the sum and difference rules were just that, okay, well, if I have a sum and a difference, I could just do them individually and then throw them all back together. That does not work for when you have a product. So I have 3x cubed times tan x. I cannot do the derivative of this one times the derivative of that one. I need this thing called the product rule. So the product rule works like this: f prime g plus g prime f. F is the first piece and g is the second piece. So when I'm finding the derivative of this function, I say to myself, f prime, what that is telling me is do the derivative of the first piece. So the derivative of the first piece, 3x cubed, is 9x squared based off the product rule. Then it says g. Well, g is just the original second function, so that's tan x. I do nothing with that except rewrite it. Then I have plus g prime. Well, what g prime is the derivative of the second function of x in our product. That is secant squared. I go back here, tan x gives me secant squared. going to leave a little space here for a reason. And then f is just our first function without doing anything to it. I'm going to put it before the trig function because that's just usually how we do things mathematically. So that is our derivative. F prime g plus g prime f. Okay? And then we have this thing called the quotient rule. So unfortunately, when you have a quotient or a division, you can't just do the derivative of them individually and divide the way that you can with the addition and subtraction rules. So we need this thing called the quotient rule. So f represents the numerator and g represents the denominator. So if we go through this, what this says is f prime says do the derivative of the numerator. The derivative of sine, if I go back here, is cosine. I'm going to put it in parentheses for now, and then I might rewrite it. Then it says just rewrite g, which is the denominator. So that's x squared plus 6x minus 5. Then I have a minus, right? The quotient rule has a minus in it. Then it's g prime. Well, g prime is the derivative of the denominator. So that's 2x plus 6, using our basic rules from earlier. Then I multiply by f, which is just the numerator, all over. This is the original denominator squared. So that's just x squared plus 6x minus 5 quantity squared. I'm just going to leave it like that. We could distribute and maybe do some simplifying, but for right now, I just want to focus on how do you do the quotient rule. All right. So anytime you have a product of two functions of x, you need to use the product rule. When you have a quotient of two functions of x, you're going to want to use the quotient rule. All right, let's move on to our last two problems of this lesson. So I just want to go over two applications of things that we were working on today. These aren't really applications of derivatives. Unit 3 and Unit 4 are really, and Unit 5 are really focused more on like going deeper into the things that we can do with derivatives. These are just some basic applications of things that you'll have to do on the AP test. So one of them is we just have a table of values for some random function. So these are the inputs and these are the outputs. And we're going to use that table to estimate the derivative of at 5. Well, f prime of 5 represents the instantaneous rate of change at 5. Well, we don't have enough information to do that because we would need the actual function to find the derivative and plug in 5. But what we can do is remember from earlier, we use the secant line to estimate the tangent line. All right, well, we took the secant line and we moved it closer and closer and closer until it became the tangent. So what we can do is our best estimate in this case for a secant line, remember secant line we need 2 points, would be the point before and the point after. So anytime you have a table, you're going to use the point before and the point after, and you're just going to find the slope. So that's 27 minus 17. So I'm just changing y over 6 minus 4. So that's 10 over 2, which is 5. Now this is just an approximation. So if you have to find the instantaneous rate of change, you find the derivative and substitute 5. If they ever ask you to estimate a derivative, that just means you don't have enough information to find it exactly. The way that you always approximate an instantaneous rate of change is you use average rate of change instead. And our best approximation is always of the given data, it's the one right before and the one right after the actual value they ask you about. So our best estimate based on this given information would simply just be 5. All right. So then the other thing I wanted to go over that uses the concepts that's really important in calculus is if you ever have to write the equation of a tangent line. There might be a lot of questions related to tangent lines and they're more about understanding, but I want to go through this example just to kind of build that understanding for tougher questions. So if we have to write the equation of the tangent line, all we've talked about so far today is the slope of the tangent line. So if you just think in general, the equation of any line could be written like this. So this, what I'm writing up here, is what we call the point slope form of a line, which you would have learned way back in algebra. And what you need, literally the reason it's named point slope form is because you need a point, x1, y1, and a slope. So let's think about how we can get those. First, let's deal with our point. Our point we know is x equals 3. If I want to find y, I just substitute 3 in. So 3 cubed plus 3 times 3 minus 8. I believe that's 28. So we're writing the equation of a line that goes through 3, 28. Well, I already can do this part of it. Y minus 28 equals some slope times x minus 3. So without doing any calculus, I've already got a lot of the problem done. The rest of the problem, I have to find the slope. Well, in algebra, you would have been given 2 points to find the slope, but in calculus, we have learned to do it only through 1 point. We find the derivative. Another notation for derivative would be y prime, and the derivative, I can use the product rule for this, the power rule for this one, 3x squared, then the coefficient of x, 3, and the derivative of negative 8 is 0. So what this tells me is this is the derivative of this. So this tells me the slope, the instantaneous rate of change, or the slope of the tangent line at any x value. Well, I want it at x equals 3. If I plug 3 in, 3 squared is 9, 9 times 3 is 27, plus 3 is 30. So I have a slope of 30 at this point. So I just throw 30 in here. And now I have an equation of the tangent line. You could certainly get this in slope-intercept form, but if they only ask for an equation, then this is good enough. I don't want you to think that's negative. That should just be y minus 28. So that's the slope of, that's an equation of the tangent line. You never have to go further unless they ask you to, or if it's multiple choice and all the answers are in slope-intercept form, then you might want to do that. But you don't want to do any extra work in, you don't want to make a mistake and then lose points. So again, this is an equation, so that is the tangent line. So that's how I'm going to leave the answer. All right, so I hope you found this lesson useful. This again is our basic differentiation. Make sure check out our TikTok, Instagram, and Facebook for all the practice problems that will go along with this unit. Please check out our Patreon where we have some extra things. We'll have an extra review and a video review of those answers. And also a live Q&A on Fridays, all right? As we build and we get closer and closer to the AP test, that is just Unit 2. Tune in next week where we'll have Unit 3, all right? I hope you found that helpful.